Good day, and welcome to CFE Media's Virtual Training Week. For this session on fundamentals of vibration-based condition monitoring, we'll be joined by Brad Hopkins, Director of Condition Monitoring, Product Management in IoT Services at HID Global. I'm Kevin Parker, an editor with CFE Media and Technology. Following our presentation, be sure and stay tuned for the live Q&A. Today's presentation can provide continuing education credits. CFE Media has met the standards and requirements of the Registered Continuing Education Program. Credit earned on completion of this program will be reported to RECEP at recep.net. A certificate of completion will be available for each participant to download upon successful completion of a test at the end of the presentation. As such, it does not include content that may be deemed or construed to be an approval or endorsement by RECEP. Get ready for an in-depth examination of vibration-based condition monitoring. Find out how the physics of vibration and mechanical systems are used in condition monitoring. This presentation is for anyone who is unfamiliar with how vibration-based monitoring works, or for those who are curious about the science of the technology. This is an opportunity to gain in-depth knowledge in a subject that continues to expand as factories and machinery become more complex and equipment downtime is more costly than ever. Attendees will learn about the following. They will have a better understanding of vibration physics. They will understand how vibration is used to detect system faults and how vibration is used to diagnose system faults. For a seamless online experience, here are some tips. Additional resources can be viewed and downloaded on the left-hand side of the screen below the session's agenda. If you would like to take notes within the session, click on the left panel labeled Notes to do so. Please remember that this session will be made live at 12 p.m. Central, 1 p.m. Eastern. Question and answer session with industry expert starts approximately at 12:45 Central, 1:45 p.m. Eastern, or immediately after the presentation ends, if it runs longer than 45 minutes. Answers will be archived within the session. You can see the Q&A details in the meeting tab on the left-hand side of the screen. Zoom invite details can be found in the additional resources tab under Q&A session. Want to take the session again? No problem. This session will be available on demand. If you're experiencing difficulties, please log out and back into the session to continue. Attendees are eligible for 1 PDH credit for this event airing on April 1st, 2021, and is categorized within the technical health and safety, including core technical category for RECEP. This event is a live educational session presented on April 1st, 2021, and on demand afterwards. Before turning to our presentation, we'd like to share a brief video from today's sponsor.
You already know that real-time predictive maintenance is the best way to monitor the health of industrial equipment and prevent unplanned downtime, but that can be expensive. Did you know that with HID condition monitoring, you can afford to monitor all essential systems in the manufacturing process? Don't stop at just expensive equipment. Protect your entire workflow with HID beacons on every machine, all with easy deployment, real-time analytics, and machine learning. See how your business can avoid costly failures with HID condition monitoring. Because isn't every asset in your business mission critical?
Welcome back. I'd now like to introduce today's speaker. Brad Hopkins is the Director of Condition Monitoring Product Management in IoT Services at HID Global. He functions as the product manager and technical lead for HID's condition monitoring product line. Brad's background is in dynamic systems, signal processing, data science, machine learning, and vibration-based condition monitoring. He received his bachelor's, master's, and doctorate in mechanical engineering from Virginia Tech in 2008, 2009, and 2012, respectively. Previous positions include condition monitoring project engineer and senior data scientist at Amstead Rail Company, Inc., as well as adjunct faculty in the Mechanical Engineering Department at Southern Illinois University. Brad, welcome to today's virtual training week session, and please go ahead.
Thanks, Kevin. So today I'm going to be covering session 2, fundamentals of vibration-based condition monitoring. And this session is part of a 3-part series. You'll recall last time, if you joined, we covered enabling predictive maintenance using condition monitoring. This time, fundamentals of vibration-based condition monitoring. And in the next session, we'll talk about using wireless sensors to improve our maintenance practices. A quick recap from what was covered in session 1. We talked about various maintenance strategies and going from a run to failure strategy where we're essentially letting equipment run until it fails without necessarily doing any inspections or maintenance, all the way up to condition-based maintenance or predictive maintenance. And recall that we covered the spectrum of condition monitoring solutions ranging from basic fault detection to very advanced prognostics, and how any condition monitoring solution in this spectrum is essentially enabling that condition-based maintenance or that predictive maintenance strategy. We also talked about a little bit more of the fundamentals of what vibration-based condition monitoring is, and gave the analogy of a dog whistle and how a dog's ear is uniquely tuned to higher frequencies, essentially has a much higher bandwidth to detect higher frequencies in vibrating air, and therefore can detect the sound of a dog whistle when a human ear cannot. And we made that analogy to vibration in rotating machinery and looking at specifications for condition monitoring hardware, with the understanding that increasing the bandwidth or the range of detectable frequencies on condition monitoring hardware is what's really going to help us to do that fault detection or diagnostics or prognostics and enable predictive maintenance. So now in the second session, I'm going to cover some more of the fundamentals of vibration-based condition monitoring, and I'm going to start with a fairly academic discussion. So it might at the beginning feel a little bit like a physics class, but I will try to keep the equations to a minimum. And I think this is going to provide a really good foundation for some of the discussions we're going to be having a little bit later on sensor specifications, and when we start getting more into the practical assessment of what a quality condition monitoring solution is and how it can help us with predictive maintenance. So let's start with a very basic system of physical vibration, something hopefully we can all relate to. So when we talk about vibration, we're talking about material properties, specifically mass and stiffness. So what does this mean? So think about a really simple setup where we have a rigid block, and this rigid block has a fixed mass, and it's just simply sitting on top of a spring. And this mass is allowed to oscillate just up and down, so it can bounce up and down on the spring. Really simple system. The stiffness of the spring itself has units of force per displacement. What that means is if we compress it or we extend it, the spring itself is going to have a force that's applied in a specific direction. And in this simple setup, we have what's called a linear spring, and that means that the force that it applies is proportional to the distance that we displace it, either compress it or extend it. So really simple system. You can imagine that if we were to compress the spring by pressing down on the top of the block and letting it go, we would see this bounce up and down about some equilibrium point. And in this simple example, this is a theoretical system that doesn't have any friction or damping to slow it down. So in this hypothetical theoretical example, we're just going to push the block down and it's going to essentially bounce up and down forever. So why does it bounce up and down forever? It's because of these two concepts of what we call potential energy and kinetic energy. When we talk about potential energy, we're talking about energy being stored in the spring. So when we compress the spring or we extend the spring, we see that the spring itself is going to store the potential to add energy to the system. So that's why when we compress it or extend it, the block's going to start to move once we let it go, because that spring has stored it as potential energy and now it's releasing it to give motion to the block. And then when the block moves, the block itself has what we call kinetic energy. And this is something that arises from the block's velocity. So as long as the block is moving, we would say that it has kinetic energy. So a quick quiz, just answer this in your head as I walk through this, see if you can figure this out and work along with me. So look at each step in this process of pressing it and letting the block bounce up and down. What are the points of maximum potential energy and kinetic energy based on what I just covered? So we said that potential energy comes from compressing the spring. So when I compress it, we have maximum positive potential energy because the spring is going to want to push that block up. Once we let it go, that potential energy gets transferred into the block's kinetic energy, and halfway through, we see the block has maximum positive kinetic energy and it's moving at its fastest speed when it's coming back through that equilibrium point. And then it's going to keep moving, and that spring is going to start to extend and pull back down on the block. And now, once again, we have maximum potential energy because the spring is fully extended, but now it's in the negative direction because it wants to pull it back down. And then this process is just going to continue where the block's going to go back through its equilibrium point. And in this theoretical example, this behavior would go on forever until we came back in and stopped it ourselves. So now we can introduce the concept of what we call natural frequency. So if we were to displace the block, push it down on the spring, and let it bounce up and down, and observed the frequency at which it bounced up and down, we would call that its natural frequency. And we can see this in everyday life. If you walked up to your car, as you may know, a car has a suspension system and one of the components is a spring. So if you press down on a corner of the car and just simply let it bounce up and down, you would see it bounce up and down at a specific frequency, and that's what we call the natural frequency of that system. Now, we can actually calculate this mathematically. If we knew the value of the stiffness and we knew the value of the mass, we could calculate the natural frequency. So it's important to understand that the natural frequency of a system is a function of its natural stiffness and mass properties. So we're talking about frequency, and frequency is going to be presented oftentimes in units of hertz. And hertz just simply means cycles per second or rotations per second. So if we displace the mass and we let it bounce up and down, and we observed over the course of 1 second that it bounced up and down 2 full cycles, we would say that 2 cycles divided by 1 second is 2 hertz. So we would see that the system has a natural frequency of 2 hertz from visualizing the system and from observing it. Alternatively, if we actually knew the properties, the stiffness and the mass, we could calculate it and we would get the exact same answer. So now let's add another layer of complexity. So instead of just simply displacing it and letting it go, we're going to now allow the base of this system that the bottom of the spring is attached to move. And let's say that we provide an input force. So we'll call that Fn. So it's an input force into the system. We're pushing on it. What we could then do is put maybe a force sensor on the top or on the mass and measure the output force. So we're giving the system a stimulus and it's going to have a response. So we're just looking at the relationship between what we put in the system and then how the system actually behaves when we give it that force input. So when we're talking about the concept of frequency response, which we're going to jump into a little bit later when we start talking about accelerometers, going back to that discussion of vibration-based condition monitoring, we can start to measure a frequency response of a system if we give it a known input at a known frequency. So now let's consider I'm going to give it a forcing function. I'm just going to oscillate the bottom at a specific force magnitude and at a specific frequency. So this would be like an oscillating sine wave. What we could do then is measure the output force of the system, and what we would observe in this very simple example where we just have a mass and a spring, what we would observe is that we're going to measure an output force, and it's going to have the same frequency as the input force, but it's oftentimes going to have a different magnitude. It could be very close to the same, it could be a little higher, much higher, it could be lower, but what we will observe naturally in systems is that the output is different from the input. And this is something interesting that we need to pay attention to understand how vibration works in much more complex scenarios. So if we have an input force at a specific frequency and the output is going to have the same frequency, if it has the same amplitude, we would call this one-to-one transmissibility. What that means is what we put in is what comes out. What we put in is being transmitted as the output. If we were to put in an input force at a specific frequency and the output had greater amplitude, it would still have the same frequency, but greater amplitude. We call this amplification because the signal is being amplified by the system itself. And then if the output has lower amplitude, once again, it's going to have the same frequency, but lower amplitude, we call this attenuation. So what we could then do is take our system and pick a range of frequencies and run this test. We could give it a known input force and measure the output force and then plot what the relationship is between the output and the input over the range of various frequencies. And in our simple example, where we just have a mass sitting on top of a spring, what we would find is that we get a frequency response curve that looks something like this. And what we'll see as we go through, we're going to get different relationships between output and input. So the question is, and work through this in your head, work along with me, what are the areas on this curve based on the definitions I gave of one-to-one transmissibility, amplification, and attenuation, and where on this plot does the natural frequency occur? So what we would see is that the one-to-one transmissibility occurs at a lower range of frequencies. So this is the flat part of the curve. What we put in is what we get out. And then we're eventually going to hit a point where this signal is going to start to amplify. It's going to peak and then it's going to come back down. And then when it drops below that one-to-one transmissibility, we get to the region of attenuation. And then based on the definition that I gave earlier of the natural frequency, what we would observe is that at the natural frequency, we would see the peak response. So when we have this scenario where our input, the frequency at which we're forcing this, if we pick that frequency to be identical to the natural frequency of the system, what we're going to see at this point is maximum amplification. And this is what we call resonance. So natural frequency itself is a fundamental property of the system. And when we force the system at that natural frequency, we get an event that we call resonance, where we get maximum amplification. Now let's add another layer of complexity to our system that's going to make this look a lot more like the real world and a little bit less theoretical. So back to our original system, if we displace the mass and left it alone to vibrate, it's going to be transforming kinetic and potential energy back and forth theoretically forever. It's just going to keep bouncing up and down. But if we placed a damper, so think of this like a shock absorber in your car, or if you have like a screen door, you know that when you open it quickly or try to close it quickly, that damper exerts a force. So think of it like that as an element that's dissipating energy from the system. So what it's essentially doing is it's taking the motion from the block bouncing up and down, it's converting it to heat, kind of like friction, and it's damping out this waveform. So in our new system, the spring mass damper system, if we pressed on it, we would see it oscillate, but it would eventually die out. So we said before that the spring exerts a force proportional to displacement, and the damper will exert a force proportional to velocity. That means the faster the system is moving, the more force the damper is going to exert on it. So back to our screen door example, if you've ever opened a screen door quickly or tried to close it quickly, you'll notice that it's much more difficult to move it than if you open it slowly or close it slowly, because the damper is actually exerting a greater force when the mass moves quicker. So now we have a representative system, still very simple, but starting to look a little bit more like what we see in the real world. We call it a spring mass damper system. And based on the way that we've defined it, we said that it's allowed to just simply move up and down. It can bounce up and down, and it can only move in that direction, the up and down direction. And because it can only move in that one direction, we say that it is a 1 degree of freedom system, or a single degree of freedom, because it only has the freedom to move in one direction. Now, if we wanted, we could define the system further and say put a spring and a damper in the left and right direction and allow it to move left and right as well as up and down. And in this case, we would say that because it can move vertically and horizontally, it now is a 2 degree of freedom system. And of course, we can't see it on the screen because it's 2-dimensional, but if we were to make this 3D, we could add a 3rd direction as well, like in real life, and then now it becomes a 3 degree of freedom system. We can also arrange this differently. So instead of giving one block left and right motion, we could restrict one block to moving up and down and add a second block on top of it and allow that to move up and down. And now, since we have 2 blocks, each only able to move in one direction, we would also say that this is a 2 degree of freedom system. So there are different ways that we could arrange our fundamental element such that we can get various forms of complexity. So in the example so far, we've been looking at a block, and this block has been rigid. So that means that it doesn't bend. If we wanted to look at a flexible body, like a long beam, and look at the way that that beam bends, we could think of it conceptually as being made up of many small elements of multiple degree of freedom systems. So this is where our system is starting to get a little bit more complex, but we can still use that fundamental building block of small spring mass damper systems occurring at small points along the way of this bending beam, and then all of it adding up together to start to form a new type of behavior, which is starting to look a little bit more like the real world. Now, in real life, our systems are much, much more complex than just a simple block bouncing or a bending beam. We would see something like a turbine blade. And what we can do to understand what that vibration behavior is run very complex simulations. So maybe you've heard of finite element analysis. And if you look at this image, what you could see is we're essentially creating a mesh, and we're breaking up this complex structure into a series of small blocks. So that's the grid that you see. And each of these blocks is going to behave sort of like a miniature spring mass damper system. And obviously, the smaller we make these, the longer it's going to take to calculate, but the more accurate our results are going to be. So what we would find then is if we ran it through some complex computer simulation, we would get a very complicated frequency response curve where we see multiple natural frequencies, multiple areas of amplification and attenuation, and it all adds together to create very complex vibration behavior. So in actual mechanical systems, you're going to have resonances that occur at multiple frequencies when they are excited. And we can think of this conceptually if you think of the classic example of an opera singer singing a specific note and breaking a glass. What is actually occurring is the opera singer has an ear tuned well enough to know what the natural frequency or one of those natural frequencies of the system is. And then if the voice is sung at a pitch that matches that natural frequency, we get that concept of resonance, where that voice input is being amplified and it shakes the glass at a greater level and it causes that glass to break. Now, going to our practical example that we are concerned with, rotating machinery, mechanical systems in a factory, what we're going to see is the system itself, the vibration starts, we get an excitation from the system rotating. So we have a shaft and say it's rotating at 1800 RPM. It's an excitation to the system. So that is that forcing function that we were talking about. And then that vibration is actually going to move through the body of the motor, which we call the transmission path. And that's that complex structure that we were talking about. So depending on the way that it's made, its structure, the materials that are used, the way that it's mounted, this transmission path is going to change. But that forcing function that the rotating shaft puts into it is going to get transformed, and it's going to look different by the time it gets to the surface where we would actually measure it. So if we put a vibration sensor on there, what we would find is that we get a very complex vibration signature that is the excitation and the transmission path itself. So the goal in vibration-based condition monitoring is basically to find out what that excitation is. So our vibration signal, it has a lot of extra noise in it, a lot of extra vibration in it. But what we're trying to find is if we have, say, a shaft that's bent or a bearing that's going bad, it's going to cause a very specific excitation. But that excitation, we can't measure it directly. We're measuring it on a point farther away from it. And the signal that we eventually get is going to have additional characteristics to it based on that structure. So our goal then is essentially to find a needle in a haystack to sort through this signal and say, what is the excitation and how can we separate that and relate it to the health of the piece of machinery? So vibration-based condition monitoring itself is its own domain, and it's the method of measuring vibration and extracting relevant information from that vibration signal and relating it to machine health. And it's a very deep science. There are textbooks after textbooks written on it and lots of techniques that we can use to understand what the health of the machine is. So now back to our discussion of an accelerometer, and we talked about this in session 1, an accelerometer being something that measures acceleration or vibration. So an accelerometer is the primary sensing element that we use in vibration-based condition monitoring. You can also get velocity sensors. Those do exist, but they're less common. With accelerometers, there are two primary types. The first is what we call a piezoelectric accelerometer. And this is oftentimes a little bit more pricey. It could be usually in the order of thousands of dollars for a single sensor, but it's going to be much higher quality, very high quality signal, very high bandwidth signal, so that one-to-one transmissibility goes out very far. It's going to have a high power input and it's going to be very low noise. So what that means is it's a very high quality signal, really good for condition monitoring. However, it can be extremely expensive. So one of the things that has happened really over the last couple of decades is the emergence of what we call MEMS sensors. And MEMS stands for micro electromechanical system. And what this basically is a silicone chip. It's a small chip. It's relatively inexpensive, very low power. It has higher noise than the piezoelectric. It has lower bandwidth than the piezoelectric, but the value cost trade-off is actually quite high. So what we're seeing is really low cost sensors. They could be on the order of dollars. In some cases, for lower performance MEMS accelerometers, they could even be on the order of cents, but very high performance for the cost that you're paying for them. And also, because they are so low power, they start to, we'll get to it a little bit later, but looking forward, they start to enable the ability to do wireless monitoring or remote monitoring because they draw so little power. So the MEMS accelerometer, it sort of behaves like our original spring mass system, where we can displace it, and that displacement will come because of a forcing function. So the vibration of the system is causing a small silicone mass to move. And when it moves, it is created in a way that it creates a voltage proportional to the input. So this voltage now is something that can become very useful to us because we can now use it in our system to start to collect a signal. So at the most very basic level, just think of this as producing a voltage that's proportional to its input. Now, what we could do is measure the frequency response of an accelerometer by giving it an excitation. So back to that frequency response curve, we could mount an accelerometer to a vibration exciter, measure its response. So if you look in the image, you see on the aluminum plate, there is a small piezoelectric accelerometer that's measuring the input of the system. And then we have a condition monitoring sensor that we're interested in understanding its frequency response. And we're looking at its value, comparing it to the piezoelectric, and then we can get a frequency response curve. So this is a real frequency response curve from a real piece of condition monitoring hardware. And we see that in this example, the bandwidth, the flat region, where we get about 1-to-1 transmissibility, goes to about 2.5 kilohertz. So that's 2,500 hertz. And when we talk about bandwidth, we typically give it an error band. So we would say plus minus 10% error. That means the transmissibility can go as low as 0.9 or as high as 1.1. But in this range, it's relatively flat. So this is essentially the useful range of this piece of condition monitoring hardware. So back to our MEMS accelerometer, we said that when we give it a force input, it's going to produce a voltage that's proportional to it. And we know that vibration is continuous. It's a continuous signal. So it's going to produce a continuous voltage signal, which is what we call our analog signal. And we call it analog because it's essentially analogous or proportional to that force input. So now we get a voltage that is proportional to the vibration of the system. Now, if you know a little bit about digital systems and sampling, you know that an analog signal won't do us any good by itself unless we actually capture specific data points from the signal. So what we'll do is we'll sample it, and this process of going from analog to digital is what we call analog to digital conversion. In other words, we're just simply sampling this voltage, logging that as a data point, and then using that in the future to perform calculations. So this process of analog to digital conversion, ADC, is usually built into a MEMS accelerometer. So if you're looking at a MEMS accelerometer and the specification sheet says that it is a digital accelerometer, what that means is it has built-in analog to digital conversion on the chip. So all of this is happening on that small silicone chip, and then you can pull data directly from it and do useful things with it. So let's talk a little bit more about sampling rate, because this is something that's going to show up on an accelerometer specification sheet or a condition monitoring solution specification sheet. So sampling rate, like frequency content, is also expressed in hertz. But when we're talking about sampling rate, hertz means samples per second. So recall that when we talked about vibration content in units of hertz, we were talking about cycles per second. But now when we talk about sampling rate, the rate at which we are actually collecting data on that oscillating waveform, hertz means samples per second. So using those basic definitions, see if you can answer this in your head by looking at this chart on the page. What is the frequency content of this waveform? And what is the sampling rate when we're taking this analog waveform with its specific frequency content and sampling it? So you can see this waveform occurs over the course of 1 second. And over this 1 second, we get 3 cycles. So 3 cycles occurring over 1 second, that means 3 hertz. So if we were monitoring a system and we saw this waveform, we would know that it has frequency content of 3 hertz. We also see that over the course of this 1 second, we're collecting 30 data points. So 30 data points divided by 1 second is 30 hertz, or 30 samples per second. So what we see in this example is that we're sampling the data much faster than the waveform is oscillating. So the waveform itself has content of 3 hertz, but we're actually sampling it at 30 hertz because we want to capture all of that motion in the waveform. So you can see in this visualization that the waveform has to be sampled at a high enough rate if we actually want to capture all of that motion. And if we take that same waveform and start sampling it at a lower rate, we're going to start missing some of those points. And of course, if the rate is too low, then the recorded data might actually be meaningless, or in some cases misleading, because what the data is showing us isn't representative of what's truly in the system. So this is why we have to understand the relationship between what's happening in our system and how quickly we need to collect data. So there is a theory called Nyquist theory. And what this essentially says is that mathematically, in order to capture the frequency of a specific waveform, we have to sample it at a frequency of at least 2 times that highest frequency in the signal. So if we take the case of our waveform that's vibrating at 3 hertz, and we sample it at 6 hertz, which is 2 times, we will capture that frequency of 3 hertz. But since we're only sampling it at 2 times the frequency content, you can see that the dotted line, what we actually capture, is not necessarily representative of the true amplitude in the signal, but we're at least capturing that frequency. Now, if we drop below the Nyquist frequency and sample at an even lower rate, what you see is that we get very misleading information. So the solid line is what's truly happening in the system. The dotted line is what we're measuring, and the dotted line is not representative of what's truly happening, and it's misleading, and it's a phenomenon that we call aliasing, because it's basically presenting to us in our data a fake frequency component that isn't actually there. So all that being said, mathematically, we have to sample at least twice the rate of the highest component in the signal. In practice, we need to sample at a rate of at least 2.56 or higher. This is just an industry practice that's been adopted over the years. But if we can, it's always a good idea to sample that signal as high as possible. And you can see when we sample at 10 times the rate, we actually get a much cleaner representation of what's truly there. So in our complex system, now you can think of it as being made of several different frequency components vibrating at different amplitudes, different frequencies, different damping characteristics. So this is back to our complex multiple degree of freedom system. So the vibration signal itself that we measure is essentially a summation of various frequency components at different amplitudes, having different damping characteristics at different frequencies, and that's what's actually in our vibration signal. So we can take that vibration signal and start doing some mathematical processing on it to try to decompose it into those different frequency components. And that's where we get an operation called the Fourier transform. Maybe you've heard of this before. But what this essentially allows us to do is break down our vibration signal into its individual frequency components. So it's taking these simple frequency components, treating them like fundamental building blocks, and by breaking it down, we can start to see what the frequency content of that signal actually is. You may have also heard of something called an FFT, or a fast Fourier transform. All that is a computer algorithm that is able to quickly and efficiently calculate the Fourier transform. So when we say FFT, we're talking about the same operation to decompose a vibration signal into its frequency components. And remember, those frequency components are important because they may be related to an excitation that is a defect in the system. So our vibration signal occurs in what is called the time domain, looking at acceleration over time. But if we do an FFT, we're transferring all of our data from the time domain to the frequency domain because we're breaking it down into its individual frequency components. And this is part of another field called signal processing, which is a very deep science. We're not going to go super deep into it today, but it's something to keep in mind that there is a lot that you can do by processing the signal in different ways to try to extract different pieces of information. But one of the most important things that you can do oftentimes is taking an FFT to see what the frequency content of that signal is. And this can be accomplished with various open source tools like MATLAB or Python or other software packages that various condition monitoring service providers or solution providers sell. Another thing that we can do, part of signal processing, is something we call digital filtering. We call it digital filtering because we are filtering frequency content of our signal. And we can break this down into three basic types. First, what we would call a low pass filter. And we call it a low pass filter because it's allowing the lower frequencies to pass and it's blocking higher frequencies. The opposite is a high pass filter, which of course does just the opposite. It blocks those lower frequencies, but it allows the higher frequencies to pass. We can also create what we call a band pass filter, which is essentially combining the low pass and the high pass filter and just looking at a specific band of frequency. So if we wanted to take a signal and isolate specific frequency content, we could do low pass filtering, high pass filtering, or band pass filtering to target a specific frequency range. So if I were to take my original signal and do an FFT on it, I would see its frequency spectrum. But if I took that original signal and applied a band pass filter to it, I would only be looking at a range of specific frequencies, and it would reject other frequency content that's below a certain point or above a certain point, just focus on a specific range, and we would see a much lower amplitude signal because we're blocking out a lot of frequency content. And then if we looked at that bandpass filtered vibration signal in the frequency domain, what we would see is that band of frequencies is targeted. And maybe in this instance, because we have some domain knowledge of the system, we know that this is a specific frequency range that we want to target, so it can help us study it. So we talked about the complexity of these mathematical operations and doing things in the frequency domain. A much simpler approach that's also very helpful that we can use concurrently is calculating what we call time domain metrics. So going into the frequency domain, it takes a lot of calculation, a lot of processing. Sometimes though, we cannot perform this type of calculation on a device itself. So if we're trying to perform local calculations, we can't afford to perform a Fourier transform. And maybe we could take raw data off that device and use a third-party software package to look at the frequency domain. But it might be more efficient in some cases to do calculations on the sensor itself. And that's where we get to what we call these various time domain metrics. Just to give an example, very simple, typically to calculate, we could look at the peak value in a signal. So we could take tens of thousands of data points and just simply pick out the peak value. We could look at what the peak value is minus the minimum value, and we call that peak to peak. Or we could perform another calculation called root mean square. And I'm not going to dig into the math of it, but you can think of this as kind of being like the average energy in the waveform. So RMS is going to use all of the data points, and it's going to kind of look at an average energy in the waveform. And this is something that is actually very useful in fault detection because it disregards specific frequency components, but it looks at the entire signal as a whole and says, are these energy levels rising? Regardless of what frequency they're occurring at, are these energy levels rising? So back to this spectrum that we talked about in session 1, we have different rotating machine faults that manifest typically at different frequencies. So we talked about how at lower frequencies, something like looseness or improper mounting will occur, something that is much higher displacement motion, something that we can see with our eyes. And then as we move up to kind of the middle range, we might have things like misalignment or imbalance. Move even higher, we might be catching a bearing going bad, but maybe very late in its life, right before it fails. If we go to even higher frequency content, now we can pick up those bearing defects probably much earlier, and then other things like gear tooth defects as well. So now this, in the light of our discussion on system frequency response and accelerometer frequency response, we can start to understand how these characteristics of bandwidth and sampling frequency are important for detecting various defects. So remember, the bandwidth is that flat period of one-to-one transmissibility. So if we can get an accelerometer that has a really flat part of the curve that goes up really high, we can capture many, many more defects. And this is why oftentimes, back to that original discussion in session 1, when we're talking about diagnostics and prognostics of expensive turbo machinery, we're going to get those expensive several $1,000s, maybe tens of thousands of dollars accelerometers that have really high bandwidth. That means one-to-one transmissibility going up to 20 kilohertz, 30, 40, 50 kilohertz. And that's going to help us pick up bearing defects right when they start to manifest themselves. For some of the lower cost sensors like MEMS, we might not be able to pick up those early stage bearing defects or gear tooth defects, but for the cost of the sensor and the value that it provides, it's quite substantial because it can be used for a fraction of the cost to still pick up a pretty good range of the spectrum of defects. So remember, we talked about taking that acceleration signal and looking at different metrics. So we could take our acceleration signal and perform calculations on it to turn it into a displacement signal, which we said was good at picking up those lower frequency defects. Velocity, more of the middle range of the spectrum, like the looseness and the imbalance, and then acceleration, typically much higher. And this isn't, in practice, it's not a clean break. Acceleration oftentimes will be really good for picking up some of those lower spectrum events as well. But oftentimes we're going to see much better performance across the spectrum by using different metrics. So one thing that's really of interest to us, back to our original discussion on kind of entry-level condition monitoring with fault detection, we use an approach where we target this range in the middle with velocity. So we see that we could use the velocity metric to pick up on a pretty wide range of defects, even though it's covering a narrow range of frequency. So we might be able to pick up looseness, misalignment, maybe a late stage bearing defect using velocity. And there has been quite a bit of research performed over the last several decades on velocity, specifically velocity RMS. So remember, we said RMS was sort of like the average energy in a signal. So if we can take our signal and calculate, turn our acceleration vibration into a velocity signal, calculate the overall RMS, we can look at how that progresses over time, and that can help us to pick up on various faults. And like I said, a lot of research has been done in this area. There are publicly available published standards that look at machines of different sizes and look at the velocity RMS levels of those machines and give indications on what the health of that machine might be. And it's not always exactly perfect. Remember, back to our discussion of false positives and false negatives in session 1, this approach, it's a threshold approach. That false positive, false negative trade-off, that is applicable in this case. So it's not a sure-proof way. However, this is a really, really good starting point for doing vibration-based condition monitoring as sort of a spot check. So we are going to dig into this a little bit further in session 3, where we start talking about using wireless sensors and using real-time data to improve our maintenance practices. We'll revisit this concept of using velocity RMS, but then also extend it to more advanced processing, talk a little bit about machine learning and AI and how we can process the data. So that will be coming up in session 3. So that concludes session 2. Thank you, Kevin, and I'll give it back to you.
Well, thanks, Brad. As a journalist, it's been fun to learn about the importance of vibration. And one thing that's interesting about it is that humans interpret vibration intuitively, but for the engineering sciences, it's a very complex phenomena.
Yes, absolutely.
Thanks, Brad. By means of your 3 sessions, attendees can get a good overview of theory and practice of condition monitoring and other emerging maintenance policies. Thank you so much for joining us. We look forward to seeing you in the live Q&A session immediately following. Be sure and have your questions ready. Thanks for joining us, and we hope the information provided will suit your purposes. Questions will be answered in a live Q&A on April 1st at 12:45 Central, 1:45 Eastern Time. Participate in the live Q&A with your Zoom invite details. These details can also be found in the Additional Resources tab on the left-hand side of the screen.